I missed it when you were talking about the data for the continuous translation case.
Yes.
Were all of the data that you discussed quantized?
For the continuous translation case, the data that I yeah. So I had like you mean this case?
Right. Yeah.
So this case, yeah, this Hall connectivity shift and angular momentum of curvature, these are all quantized. There's a fractional part which comes from the fractionalization, and there's an integer part which comes from this H3. So, but yeah, these are all quantized values.
Because you're using this Borel cohomology, or something like that, some generalization of that. And in general, when you have non-compact groups, this doesn't have to give you quantized classifications. So there was a danger maybe that you were going to get something non-quantized, or
yeah. So okay, yeah. So I was debating making this point or not. So you're right that when you have these non-compact continuous groups, you might find a situation where you calculate H3 and like maybe it's continuous or something. I don't know. And then, or it could be that the solutions of the G cross braid tensor category have a continuous parameter. And if you find that, then it seems physically reasonable that you should just consider the moduli space of such G cross solutions as describing one specific SET phase. But in this example, everything is discrete. This is the result for this Borel group cohomology. It's just this Z cubed. So in this case, this issue that you're concerned about just doesn't come up. It might come up for other groups, I don't know, but in this case, it doesn't come up.
Yeah, and maybe the Borel cohomology isn't exactly the correct classification in all cases. But anyway, I'm not sure.
Yeah, it may not be. So, but the comment I have about that is I don't know what other possibilities to consider besides piecewise continuous and measurable. And in this case, they're just the same. But I mean, you're right that perhaps for other groups, these two are inequivalent and we don't know which one to use. Or perhaps there's even yet another possibility I didn't consider that we should consider.
Right. I mean, you can go to the more abstract math definition. Then, I think the general answer should be, you classify maps from the classifying space of a group into the some space which is defined by the TQFT. Anyway,
well, but it's not. I mean, I don't know how to actually define that. What I know how to do is write down G-crossed equations and data and like solve them, and then it's up to me how I define the properties of that data, the continuity properties of the data.
Yeah. Cool.
Done. So I have a question for Maissam. You have the finite number of possible fractional quantum Hall state, right? That's the end.
Yeah.
But maybe my question is stupid. But for example, if you consider the Jane sequence, you have like many different shapes. So how can you like classify them? Because like, for example, the Jane state can be the filling fraction n divided by 2n plus 1. And with the different value of n, you can have different when G shifts. So how can you restrict the number of total different?
Well, okay. So what I'm doing in this table is I'm fixing the base topological order. So I'm fixing the modular tensor category, and then furthermore, I'm fixing certain this is only for this lattice case. So here I'm fixing the integer part of the Hall conductivity. And I'm fixing the integer part of the filling fraction and the integer part of the angular momentum filling. So once I fix these integer values and I fix the base topological order, then I still have this. Then I have this finite set of different possibilities. So in your situation, you could say in the continuum, well, the shift can be like I can add any integer to the shift. So yes, there are an infinite number of possibilities. So here I'm fixing the infinite part. And then looking at whatever residual finite possibilities there are.
Thank you.
Matt?
I have a question for both. First from Mike. When you say the line symmetries act as a symmetry fractionalization, like here in this case, that the symmetry action is sort of on the charge is like a real representation, but you're saying so you're saying symmetry fractionalization is different from some projective representation. Is that
well, I
the
mean,
points you're making?
Right. I mean, I think you mean linear representation.
Linear representation. Yes.
But yeah, I know what you mean. Yeah, I think it's right. So it's certainly, okay, so here are some simple things that I can say. So one simple thing you can say is that if you look at one of the E excitations and you ask how any particular subsystem symmetry generator acts on that excitation, you just pick one generator and you ask how it acts. It acts on it in a linear representation. Nothing is fractionalized. And in fact, you can't tell that anything is fractionalized if you pick any finite subset of generators and you ask how they act on your excitation. You have to look at all of them. And so it is true that now there are some options for how you actually want to define the symmetry group if you really want to work in infinite space, and it becomes pretty subtle because you might choose your symmetry group to involve any infinite product, possibly infinite product of the generators, or you might restrict to only finite products of the generators. And for a local Hamiltonian, it doesn't really matter actually, because the ladder group is smaller, but if a local Hamiltonian is invariant under that ladder group, it has to be invariant under the former one too. So it gets pretty subtle. But in either case, I think the representation here is actually linear. So you need to characterize it in a different way. I think the right way to characterize it is probably something like you say that your symmetry group is finite products of the generators, but you have to specify some additional information, which is how the symmetry actually acts on local operators. And that, there are certain operators that carry a single row charge and a single column charge, and other local Paulis are uncharged. And somehow that you need that kind of information to tell that this is symmetry fractionalization. So, I mean, but yeah, the bottom line is it's a little weird because there is definitely the property that you cannot neutralize these E particles, but it's, but it doesn't seem to fit into the mathematical framework that we're used to.
But Mike, it's almost like a projective representation, right? Because
it's almost like a projective representation.
What you're saying is that if you take the product of all the row operations, it's equal to the product of all the column operations. That's essentially the origin of why you said that local excitations can't have charge under one but not the other, right? Because actually the product is the same.
Right,
but,
that's true.
And then so you're saying that this group all kind of fails up to a phase factor.
That's right. So that group, that relation in the group fails up to a minus sign. That's one way to think about it. But I'm not sure that that's the best way to think about it because, well, okay, that needs to be supplemented with something else, because if you think about that within the standard group cohomology framework, that minus sign is not robust because you can kill it with redefinitions. And there's a physical reason that you should not allow for those redefinitions, which is that, if you look at a single subsystem generator, the region on which it acts in the ground state and on some state in the E sector can be exactly the same. The density matrix of that region can be the same. And so there's sort of a canonical relative phase choice of that operator in the trivial sector and the E sector. So those redefinitions are to some extent not really allowed here.
You just need a new definition of group cohomology somehow, right? It takes that into account.
That would be, yeah, I mean, I think ultimately that would be nice. That's what would be nice to have, but I don't know how to do that yet.
Okay, thank you. And then a question for Maissam. So when you calculate these cohomology classes, do they automatically give you these generators of the group, like these responses, or do you have to sort of match them by hand?
That's, I mean, you can calculate these cohomology groups by kind of abstract methods like, you know, Linden,
Right.
Hochschild, spectral sequence, and so on. So then you do have to do quite a bit of work to, like, so then, like, you know, find representative co-cycles, then figure out what they actually mean. So there's a significant amount of work in, yeah, getting the physical interpretation from after just computing the cohomology group abstractly.
So it doesn't come out automatically.
No, not really.
Thank you.
Andre?
Yeah, thanks. So Mason, I have a question for you. Can you show the slide where you had these three responses for the continuous spatial and spatial symmetries?
Yeah, I'll try. Let's see here.
It had an effective action on the bottom. Yeah, this one.
Yeah.
So when we were working on this, there were two cases that quantitatively were different when it comes to this action, and we could never really figure out what's the origin of the difference mathematically. So if you look at your action on the bottom, there are 4 terms. So let's look at first 3, right? These first 3 are the spatial, or, you know, come from the symmetry, the responses. So there are 2 cases for these first 3 terms. It's either a full square or it's not.
Okay.
So you can, if you introduce field A plus some kind of coefficient omega, this thing either becomes a full square or it doesn't. And that depends on the values of these 3 coefficients of sigma h, s, and ls.
Right.
So for every single state that comes from a conformal field theory, this is a full square. For every state that we really could put our finger on except the Jane series, this is a full square. So I was wondering if in your kind of much more sophisticated approach, do you see what's special, what's different between these 2 cases?
I mean, that's an intriguing question. No, from our approach, I wouldn't see anything that is different. You'd have, probably there's something about, you know, the wave functions coming from some holomorphic correlator of chiral CFT that gives you that, but I don't think, like, it's not obvious how to track down why that would, where that shows up in this kind of algebraic scheme.
So this imposes the relation on sigma h, s, and ls. So if I postulate the relation, does it would it restrict something, anything?
If you postulate a relation between sigma h, s, and ls, but then you're kind of presupposing the answer. I mean, I think that there seems to be an interesting question of, like, how do you determine from this data, from this algebraic characterization, when something comes from a chiral CFT, which maybe there's a way, maybe there's some way to do that, but I don't know what it is.
Okay, yeah, thanks. That was the question.
Okay. I don't see any more hands. So Nati, okay, that seems to be answered. Okay, if there are no more questions, we can thank the speakers and wrap up for today. Thank you.
Thank you.